Okay, so this is next topic is steady evaporation of liquid droplet. Okay, so now let us see the steady evaporation of liquid droplet. Okay, here vaporization of liquid fuel droplet is of a practical interest. So, as I told you, no, the liquid fuels cannot be used directly like you feed the gaseous fuels. So, in order to increase the vaporization rate, we atomize the liquid into several droplets, and so the rate at which a droplet, single droplet, liquid fuel droplet vaporizes in any medium. So, that is what is of interest to us. So, a simplified problem, let us consider a quiescent environment where there is no bulk flow, convective flow is not there. Okay. Heat from ambient, so the temperature at the ambient side is higher than the boiling point of the liquid, slightly higher than the boiling point of the liquid. So, the heat from the ambient supplies energy to vaporize the liquid. So, that is what the situation is. Okay, now the vapor is transported from the droplet surface, into the ambient. Now, again ambient has a species B, just like the Stephen problem where liquid A in the test tube was evaporating and the liquid A surface was maintained constant here. Okay, that is the x equal to 0 was maintained constant by supplying the liquid slowly at the rate at which it was evaporating, and the A mixed with the inert species B, similar to the droplet vaporized into a inert species B. Okay, so this is the scenario. Now, what we want to achieve here is we have to determine the mass flow rate of the vapor from the droplet surface, then the time history of droplet radius in some manner. Okay. So, how the radius, now here we are trying to see a problem where the droplet radius initially has some value and by evaporation the droplet radius shrinks. Okay. And finally it will become 0 when all the liquid is vaporized. Then what is the time for that droplet lifetime for a given droplet of initial diameter, say 1 mm, to completely evaporate in a given environment? What will be the time? So, that is called droplet lifetime. So, we are interested in the three quantities here. In the previous one, the steady evaporation rate was the only thing what we saw in the Stephen's problem, because we are supplying the liquid at the same rate at which it evaporates. So, the liquid level was maintained at a constant location x equal to 0. Okay, steady problem. Here actually this appears to be an unsteady problem, correct, because we are now looking into time history of the droplet radius. Initially having some initial radius value, then goes to 0 at the end of the droplet lifetime. So, what is that time? So, based on the temperature, based on the fuel, and based on any other parameters like convection if it is present. Now, in this case we are going to look into only the quiescent environment. So, okay, now simplified problem of droplet evaporation, but this is in spherical coordinates. So, what we call a spherically symmetric coordinate. Okay. So, here the radius is the only coordinate direction. So, for example, if there is a droplet, okay, droplet and so this is center and this is the radius. This radius is r, that is going to be changing with time, as a function of time it will change, correct. This radius is going to change with time, and at any point in time you can see that the vaporization, the vapors will evolve normal to the surface all over the droplet. So, that within a time duration delta t, some mass dm of the droplet will come out, so that the radius changes from r1, it decreases to r2. So, this is what the phenomena is. So, the droplet, spherical droplet. So, if we track only one radius, that is enough for us. So, that is the way we are considering this problem as a one dimensional problem at any radius in any theta or phi, correct. So, in a spherical coordinate, radius, theta and phi, there are two angles and one radius, this r. So, these are the 3 coordinates, and we need not even worry about other 2 coordinates, because take any radius, radial direction, okay, there at any particular time some mass has come out. So, we can just integrate this to the entire droplet surface. So, only coordinate what we consider is the radius, and at any time instant how the what is the radius value, that is what. So, that is r is a function of time. Okay. So, at the surface the radius is also rs, okay. Here instead of say r we can say rs, or maybe rs equal to r of t, rs which is going to vary, surface, the radius at the surface is going to vary as a function of time. Okay. Now, again the similar nomenclature for the mass fractions. Here I am saying it is a liquid fuel. So, YFS is the mass fraction of this liquid at the interface or the surface of the droplet, and at a very far distance it will be YF infinity. Okay, you are considering this ambient. So, this is evaporating into a big ambient here. This droplet is evaporating into a big ambient. So, here this will be YF infinity, and here it is YFS, okay, and RS varies as R of t. Okay, now it is a transient process, but I do not call it as a transient, I just call it what is called quasi-steady. Okay. Why is it quasi-steady? Because even though there is a vaporization, like the shrinkage in the droplet diameter or the radius that reduces from initial value to 0, the rate at which it is decreasing is not going to vary. Okay. So, that is the important assumption made here. Okay. At any instant in time, the process is assumed to be steady state. That is, the rate of vaporization calculated in some manner is steady. That is one of the important. How it is going to be steady, we will see. Okay. Now, the liquid temperature is uniform. It is like maybe the droplet diameter is not so huge, some finite smaller diameter, so that the liquid temperature is uniform, or it has gone through a initial period of heat up. As I told before, the Qi to L interface to the liquid part is initially predominant, but after a very small time period, okay, then that becomes very minimal, and whatever heat comes from the gas phase to the interface predominantly supplies to the latent heat of vaporization. So, in this basically the liquid temperature becomes uniform, that is, the heat up period is over and surface has already reached a temperature which is wet bulb temperature. That means it will not vary, the surface temperature or the liquid temperature will not vary after a particular time period, small time period it will take to reach that condition. After that condition it will not vary. So, the transient droplet heating period is very less when compared to the entire droplet lifetime. So, let us take 1 mm droplet diameter initially, okay. Then this 1 mm droplet diameter initially at 298 Kelvin, and the boiling point let it be say 371 as I told in the previous example. So, now to increase the temperature from say 298 to say 365, something like that, that is the temperature which is finally attained. So, that time period is much lesser when compared to the droplet completely vaporizing from 1 mm to 0. So, the entire droplet lifetime is higher, much higher than the heating period of the droplet, which will take its temperature from 298 to the very close to the boiling point. Similarly, vapor liquid equilibrium, this is called local thermodynamic equilibrium. So, that I told you this P versus T, this curve is going to be for any particular temperature there is a definite saturation pressure or local thermodynamic equilibrium that prevails at the droplet surface. Then all the properties are constant near the droplet surface. So, whatever property you want to use, say rho, d, this product, etc., this is constant. This is assumption we already made. So, These are the assumptions we have. See, any theoretical calculation involves such assumptions to bring down the complexity of the problem. Okay. So, one dimensional. So, Rs is going to vary as a function of time, and I am going to decrease from Rs initial to 0, and at any point based upon the surface temperature is constant now. So, a definite value of Yfs is going to be there, and that decreases to a very low value of Yf infinity when you go far away. So, as R tends to R infinity, Yf tends to Yf infinity. So, this is the condition. T infinity is the ambient temperature is greater than the surface temperature, so that it will aid in evaporation. This is the problem in hand. Now, exactly what we did for this Stephen problem, we are going to do in a spherical coordinate, the mass conservation. Okay. So, again you can see the fixed law coming to help us. So, the net mass, this is the rho f Vf fuel, there we wrote rho a Va, here we are writing rho f Vf equal to rho V times Yf plus the diffusion part rho dFb. Instead of dAb, we are putting dFb into the gradient of Yf with the only coordinate r. So, that is the flux that multiplied by surface area, that will be the mass flow rate kg per second into meter square, that will become this. Okay, that will become kg per second. So, this is the flux into area. Okay. So, that just multiplying by 4 pi r square. Now, again you can see that the inert species will not go into the droplet. At higher pressures it is possible, but we are not considering that situation here. The pressures are very low and more moderate. So, Vb, the inert species velocity is 0, so that the bulk velocity or bulk flux, mixture flux is nothing but this. Okay. Substituting this in this, you get this, the mass flow rate of the vapor from the interface or the droplet surface to the ambient is given by minus 4 pi r square rho dFb divided by 1 minus Yf into this. So, this is what you get. Now, you can separate the variable, and please understand what I told you, even though the problem is transient in hand, the rate at which the evaporation takes place is constant. Okay. So, that is what the problem is quasi-steady. See, even though if you take a car which is moving from point A to point B with a uniform velocity, okay, even though it is moving spatially, it is moving from one location to another location, the acceleration is 0. Similar to this, here there is no time dependence for the, so there is no time dependence on velocity there. Here there is no time dependence on the rate of vaporization. Even though r, the radius of the droplet varies with time, the rate at which it does, mass is evolving from this, that does not change, that this is a constant. So, keeping that in mind, we can write, so integrate this equation and apply the condition at the interface Yf of r equal to Rs is Yfs, and if you apply that condition, you will get the expression for slightly complicated expression than what we saw in the Cartesian one dimension. Here the spherical, you get this expression. So, Yf at any radius in the gas phase, please understand, we are not interested in the liquid phase. Yf from this, so I am trying to plot this variation here, what I have shown here, this variation of Yf s to Yf infinity, this is given by this expression, where the mass flow rate of the vapor is constant, rho dB is taken constant. Okay. And this is at any r, and this is given surface. Okay. So, this is at any r in the gas phase basically. So, this is from the surface, and this r can be Rs. So, this r actually varies from Rs to R infinity. You can put any value there in this, and at Rs it is Yfs, and if it goes to R infinity, this will tend to Yf, this will tend to Yf infinity at R tending to R infinity. Okay. So, this is the way this profile what I have plotted here is mathematically represented as this. Okay. Now, the evaporation rate can be found like this. This is a very important expression. Now, I substitute y equal to y of infinity at r equal to r tending to infinity, okay, r tending to r infinity, r tending to infinity. See, you need not take infinity, you can take a high value of r called r infinity, r suffix infinity. Maybe it may be say 100 times the droplet diameter and so on. It need not be 100 times, it may be say 50 or 80 times based upon the flux which is coming out. So, the mass flow rate of the vapor is 4 pi r square at a given frozen diameter or radius Rs is given by 4 pi Rs into rho, but at every Rs it is constant, please understand that, rho dfb into natural logarithm of 1 minus yf infinity divided by 1 minus yf. Yes. So, this is a similar equation what we got here. Here you can see the mass flux for the steepness problem, similar expression we got, but we have put mass flux here, but here we are multiplying that with the surface area to get the mass flow rate or evaporation in kg per second. So, now this natural logarithm term, I am see following Spalding's approach, we can write this term here as 1 plus by, okay, 1 plus by, where this by is called transfer number or say mass transfer number. In this case we can say mass transfer number. 1 plus by is written as this, 1 minus y of infinity divided by 1 minus y of s. So, this is also called B number by Spalding. So, this actually shows how the evaporation, B number is higher, the evaporation rate is higher. Actually speaking, this term rho into dfb dictates evaporation in a much more predominant manner, because this appears in this natural logarithm term. Even if you increase by say 5 times, since natural logarithm appears, it is not going to increase the mass evaporation rate. But if there is an increase in the df or rho into df, this product, then you can see that there will be much more increase in the mass evaporation rate. Okay, now we have to find what is called evaporation constant, because this is a constant scenario. No, how this evaporation is assumed as constant because of this. So, let us try to do this. So, let md, okay, md be the droplet mass at any time instant. Initially it is due to the entire droplet diameter, initial droplet diameter, then finally this is going to decrease to 0. So, the rate of the variation of md with time is nothing but negative of the mass evaporation rate, m dot minus m dot. Okay. In turn, md, the mass of the droplet, can be written as liquid density into pi by 6 d cube volume. So, density into volume of the liquid droplet. So, this, please understand that d is nothing but 2 times Rs, Rs is a function of time. So, that means d is going to be a function of time. So, obviously, so this, now substitute here d, capital D by dt will be written in this way, because you know the expression for this. So, using this expression and using this, I am writing this. So, rho 4 times rho dfb by rho ld minus of the into natural logarithm of 1 plus by. So, now take this d to this here. So, d capital D square by dt will be equal to 8 rho dfb by rho l into natural logarithm of 1 plus by. Okay, now this you can see the right hand side. We have already assumed rho into dfb as constant. So, this is constant and this is constant and this is also constant. When t is a constant, okay, for a given, see, for a given t infinity, okay, Ts is constant. Given t infinity, Ts is constant, because we are assuming that the wet bulb condition is reached. So, now based upon this you will get the right hand side to be constant. That means that the rate at which the square of droplet diameter changes with time, rate of droplet diameter changes with time, that will be a constant. The time derivative of the square of droplet diameter or the droplet surface area we can say is a constant, and slope of this, okay, that will be, so if you integrate this d square by dt, take dt to the other side, and this is a constant. So if you take this to the other side and integrate this, slope of that equation will give you the evaporation constant as this. Okay. So K will be equal to 8 rho d Fb divided by rho L into natural log 1 plus By, and pictorially you can see that initial droplet diameter is d naught square, finally it goes to 0, and this entire process occurs in a constant slope, with a constant slope, that is a straight line. So this slope is nothing but the evaporation constant. Okay, and the time at which this droplet from the initial diameter goes to a 0 value, that is the droplet lifetime. So Td is the droplet lifetime. Okay, so now that is what we are going to put here. So this is this type of writing this, no, so integrating this d square at any time will be equal to d naught square, that is the initial droplet diameter square, minus K is the evaporation constant time that is called d square law. It is very important. So if you have a droplet which is vaporizing under thermodynamic equilibrium condition, you will see that the droplet surface area or the diameter square will be, the variation of that with time will be a constant, that is called evaporation constant, and using that we can calculate the droplet lifetime and so on. So this is very important. So the d square law is obeyed because initially, see, there will be only some changes during this or during this part, there is some small variation predominantly. So for example, excluding this small times, okay, here I am hatching here, excluding these small time periods here, most of the time period here the evaporation will be steady. That means it will be a straight line. Here there will be some changes, here there will be some changes later, towards the end there will be some changes in the slope. Initially there will be some changes in the slope. Apart from that, say we can say 80% of the Td will be steady. So d square law is valid for around 80% of the droplet lifetime. So that is, so we can just use that for calculating the evaporation rate of a droplet. Please understand that here important thing is you should understand that the Ts is constant, Yfs to be constant, Ts should be constant, and the Ts depends on T infinity. Ts is, see for example, Ts is close to boiling point, but how close it is to the boiling point is determined by the value of T infinity. Okay. So this is very important. So we have to understand this. So for example, if Ts is, see boiling point is say 371 and Ts is only 372, then Ts will not be very close to 371, it may be say 350 something, 350, 360 something like that. So we have to really determine. So how the Ts is dependent on T infinity. We are assuming constant Ts based upon T infinity, how it is. So based, once Ts is calculated, Xfs can be calculated. From Xfs, that is the mole fraction, mass fraction can be calculated. So then everything is as per our assumptions. Then we can solve these equations. Okay. So let me stop here. So a droplet, even though there is a change in the diameter, the rate of vaporization is a constant obeyed by this particular graph. So that is called d square law. So we can apply this for several scenarios. So let us see some worked examples for the mass transfer topic. So the first example here, so consider liquid N-hexane in a 50 mm diameter graduated cylinder. The distance from the liquid gas interface to the top of the cylinder is 20 centimeters. The steady state N-hexane evaporation rate is 8.2 into 10 power minus 8 kg per second, and the N-hexane mass fraction at the liquid air interface is 0.482. The diffusivity of N-hexane in air, the binary diffusivity, mass diffusivity of N-hexane in air is 8 into 10 power minus 4 meter square per second. So, what is asked is determine the mass flux of N-hexane vapor, then determine the portion of the flux associated with the bulk flow at the liquid gas interface, then evaluate the diffusional flux of N-hexane vapor at the liquid gas interface. So, these are the three things which you need to find. So, you can see that the evaporation rate is given 8.2 into 10 power minus 8 kg per second, and the mass fraction at the interface is given. So, this is the YAI. So, A is hexane, okay. A is the liquid hexane, and YAI is given. This is the m dot of A, okay. So, that is given in kg per second. Okay. So, now first to determine the mass flux of N-hexane vapor, mass flux, you know that mass flux is nothing but the mass flow rate of the vapor from the interface to the gas phase divided by the area. Now, the area is AS, area of the surface, liquid surface is nothing but the area of the graduated, the cross section area of the graduated cylinder, okay. So, diameter of the cylinder is given as 50 mm. So, pi d square by 4 and substitute in meter, 50 mm is 0.05. So, that is the area here. So, the mass flux is nothing but the mass evaporation rate divided by area of cross section, which is 4.176 into 10 power minus 5 kg per meter square second. Okay, so, that is the flux. This is the total flux which is coming out of the liquid gas surface interface. Okay, now, so you know by Fick's law, so this mass flux is nothing but rho A V A. Okay, so now by Fick's law, you know m double dash, that is the rho A V A equal to rho A into capital V into YFS. Now, this rho A V capital V will be equal to rho A V A, because that is the liquid only evaporates, there is no solubility of the gas in to the liquid phase, minus the diffusion part is rho DFS. So, rho DFS into the gradient DYFS by DX. Okay, now, the bulk flux or the total flux contributed by the convective part, convective part is m double dash into YFS, the first term. So, that is nothing but m double dash is 4.176 into 10 power minus 5 kg per meter square second into the mass fraction of the fuel at the interface. Okay, this is given here as 4.482. So, substitute that, you will get 3.952 into 10 power minus 5 kg per meter square second. The diffusion flux is the other component minus rho DFS DYF by DX at the surface will be nothing but the total flux minus the convective flux, which is equal to 4.176 into 10 power minus 5 minus 3.952 into 10 power minus 5. So, that is 2.24 into 10 power minus 6 kg per meter square second. So, that is the answer. So, a simple problem. Okay, next worked example, consider water in a 25 mm diameter test tube evaporating into dry air. So, you have a water, here the liquid water, with 25 mm diameter. So, the diameter is 25 mm of the test tube, and it is evaporating into atmospheric pressure of 101.325 kilopascals, and the temperature is 25 degrees, that is 298 Kelvin. The distance from the water air interface at the top of the tube, that is L, is constant, equal to 15 centimeters. So, this is the top of the tube. So, from this to this interface, which is L. So, L is given as 15 centimeters. The mass fraction of the water at the water air interface. Okay, so this is given as, this is the YWI. Okay, mass fraction of the water at the interface is 0.0235, and the binary diffusivity of water vapor into air is 2.6 into 10 power minus 5 meter square per second. Okay, this is so D water air equal to 2.6 into 10 power minus 5 meter square per second. So, these are the given data. So, determine the mass evaporation rate of water, determine the water mass fraction at L by 2, x equal to L by 2. So, this is the x direction now for us, the Stefan's problem. This is the x direction. So, the x equal to 0 is the interface, x equal to 0 is the interface. So, at half of that gas phase height. So, L is the total height of from the interface to the top of the cylinder or test tube. Now, at the half of the location, what will be the mass fraction of the water? Then determine the fraction of the water mass flow that is contributed by the bulk flow and the fraction contributed by diffusion at this length at x equal to. So, once from the interface the convection of the evaporation is happening. So, now how the water vapor is distributed the midway of this column. So, what is the fraction of the mass flow at the location of L by 2 contributed by the bulk flow, that is convective part, and contributed by the diffusion. Now, the mass flux, we have derived this. Mass flux is rho s dw. So, dwr. So, I have just in short written as dw divided by L into natural logarithm of 1 minus yw infinity, which is in the top of the tube, let us take, divided by 1 minus ywi, that is the interface mass fraction here. So, now it is given that it is dry air. Okay. So, evaporating into dry air. So, that you have to keep in mind. Okay. So, now what is the so at the interface you can see that the water mass fraction is water vapor mass fraction is 0.0235. So, remaining should be air. Okay. So, mass fraction of air will be 1 minus mass fraction of water, that is 0.9765. Okay. Now, molecular weight of mixture, you know the molecular weight of water and that of air. So, molecular weight of mixture is 1 divided by mass fraction of water divided by its molecular weight plus mass fraction of air divided by its molecular weight. So, you get 28.44 kilogram per kilomole, that is the molecular weight of the mixture. Now, what is specific gas constant of the mixture at the interface, that is gas state of the interface, is 8.314 universal gas constant divided by the molecular weight of the mixture, that is 0.292 kilojoule per kg Kelvin. Okay, now density is P by RT, that is this 1.165 kilogram per meter cube. Okay, now you have to find the mass flux. We substitute here in this equation 1.165 density into, this is given as my binary diffusivity, that is 2.6 into 10 power minus 5 divided by L is 15 centimeter, that is 0.15 meter, into natural logarithm of 1 minus 0. So, dry air prevails at the top. So, y water infinity is taken as 0. There is no moisture or anything there. So, dry air. So, that is so this is the yw infinity, that is taken as 0, and so ln of 1 minus yw infinity divided by 1 minus ywi. So, this is ywi. So, substituting this, you get the mass flux as 4.8 into 10 power minus 6 kg per meter square second. Okay, then mass evaporation rate, that is asked. That is nothing but the mass flux into area of the cross section of the test tube, that is the mass flux times, this is pi d square by 4. So, this is d square. So, pi d square by 4. So, you get 2.36 into 10 power minus 9 kg per second. Okay, now we need to determine the mass fraction of water at L by 2 location. So, from the total column height is above the interface is L. So, L by 2 location. So, let us first find the water mass fraction, water vapor mass fraction as a function of x. Okay. So, that is given by 1 minus ywi into exponent of mass flux into x divided by rho dw, correct. So, now these are other things are constant here. So, you substitute this, you will get the x here, the m double dash into x. So, this is the variable. So, at the location of x equal to L by 2, substitute x equal to L by 2, that is 0.15 by 2 here, and get the mass fraction, that is 0.0118. Okay. Now, what is asked? So, as you can see that the mass fraction from 0.0235 at the interface decreases, at L by 2 it is 0.0118. So, now apply Fick's law, m double dash equal to m double dash y w at the interface minus rho dw into the gradient dy w by dx at the interface. So, actually you can divide this throughout by m double dash, so that you get this equation 1 equal to yw at any location you can put now. So, rho dw by m double dash into dyw by dx. So, now it is clear that the mass fraction, the mass flux fraction due to bulk flow is yw. Fraction, you are dividing that by the mass flux. So, mass flux fraction, so this is the component due to convection and this is the component due to diffusion. So, this added together you get 1. So, that is the fraction. So, this yw is the fraction of the mass flux due to bulk flow. So, that will be 0.0118 at L by 2 at x equal to L by 2. Similarly, the component due to diffusion should be 1 minus yw, that is equal to this. You need not evaluate this, it is 1 minus that, correct. So, that will be equal to 1 minus 0.0118. So, you get the component due to the diffusion is 0.9882 and due to the bulk flow convection is 0.0118. Okay. So, this is the second problem. The third problem, calculate the evaporation rate of 1 mm diameter water droplet. Okay, 1 mm diameter water droplet. Okay, so this is 1 mm diameter water droplet at 75 degrees evaporating into hot air at 500 Kelvin. So, the ambient is at 500 Kelvin, the droplet temperature is 75 degrees centigrade and the ambient pressure is 1 atmosphere. The saturation pressure of water at 75 degrees centigrade is 38.58 kilopascals. Okay. So, P sat at 75 degrees centigrade is 38.58 kilopascal, that is given. And the diffusivity of the water vapor into air is, so it's at an average temperature. Please understand that ambient it is it at 500 Kelvin, but the water is at 75 degrees centigrade. So, the diffusivity is a function of temperature. So, as the temperature varies, the diffusivity will vary. So, this diffusivity is reported at an average temperature, which is 500 Kelvin plus 75 plus 273. So, this divided by 2. So, this is the average temperature at which this temperature plus this temperature by 2, that will be the average temperature at which this diffusivity is calculated and reported here. Now, mole fraction of water at the interface, correct. So, at the interface, this is interface. So, mole fraction of the water at the interface I is the saturation pressure at the liquid temperature divided by the total pressure. So, what is the saturation pressure? It is given at 38.58 kilopascals at 75 degrees centigrade divided by the total pressure is 1 atmosphere, written in pascals 101.325 kilopascals. So, both are kilopascals. So, you get the mole fraction of water as 0.381. Okay. Now, molecular weight of the mixture. So, once the mole fraction is known at the interface, the rest should be the air. Okay. So, now what is the molecular weight in the molecular weight of the mixture? Sigma ximi, that is 0.381 into 18 is the molecular weight of the water vapor. Molecular weight of the air and its mole fraction is 1 minus that of water, that is 0.381. So, you get the molecular weight as 24.71 kilogram per kilomole. So, now mass fraction of the water at the interface calculated. So, now molecular weight of the mixture is known and the mole fraction is known. From that you can calculate the mass fraction of the water at the interface, that is 0.381 into 18 by molecular weight of the mixture 24.71, which is 0.278. So, now you calculate the values. Okay, B number you calculate first, YWS minus YW infinity divided by 1 minus YWS. So, again YW infinity is taken as at a far of radius, it is taken as 0. So, very close to 0. So, taken as 0. So, now 0.278 is the interface mass fraction of the water vapor minus 0 divided by 1 minus 0.278, that is 0.385, that is the B number, By. So, you know here B is calculated here, By. Now, you know rho, you know DFB, rho L is known. So, calculate here gas phase density. Now, again gas phase density you have to take average, because as I told you, see this property diffusivity is calculated at an average temperature, that is 500 Kelvin plus 75 degrees centigrade. So, here also you have to calculate the density. So, gas phase density is the average value between the interface and the ambient. So, interface temperature is 75 degrees centigrade, ambient temperature is 500 Kelvin. So, try to calculate that. So, at the interface, what is the density of the interface? Molecular weight into pressure divided by universal gas constant into the temperature 75 degrees. So, 75 plus 273. So, that is the density at the interface. At the ambient, you know, only air prevails. So, air's molecular weight, this is the mixture, interface in mixture is prevailing. So, this is mixture molecular weight you have to substitute here. But at the infinity, only air is present. So, molecular weight of the air into its pressure divided by RU into the temperature of the ambient 500. So, this is, so the average density is taken here. Substitute average density, D is known, average D is known, then rho L is 1000, is liquid density. So, substitute it, you get the K value. K is nothing but the evaporation constant. Okay, that is the D square law. So, you know the D square law. So, this K is the evaporation constant. Okay, that is in meter square per second. So, that is what get. So, that is what is asked.